All right, so welcome to class for Monday. Today is the 27th of April. Today we're going to be talking about angular momentum, which is how figure skating works, among other things. So let's see, there's my cursor. All right, so we are officially at the 2-week mark left in the semester, which I don't think could possibly be right, but the calendar insists that it is. So we have this week and next week, and then of course finals week. As a reminder, the due date, the hard due date for everything in this class is Friday, next Friday, right? That's May 8th, next Friday. I need everything done, everything turned in, completed, everything you want graded next Friday. So I thought I'd do a quick rundown on what is left in the class. So for Wiley Plus, you have a chapter 11 homework and adaptive practice. For chapter 13, you only have the adaptive practice. I'm not going to give you a homework on the harmonic motion because unfortunately we just don't have time to do it justice. But I do want you to do the adaptive practice because it'll help you. Harmonic motion is a concept that you need to see at some point. That's for Wiley Plus. Now, the Wiley Plus deadlines keep rolling. So for example, chapter 11 homework and adaptive practice are shown to be this Friday, along with everything previously that we've had due in Wiley Plus. I have to do that because the system will only regrade things once a deadline has passed. So they will be due this Friday, and then I will bump the deadline back to next Friday for all of this stuff. Okay, other things. So that's Wiley Plus. Perusal. There are 2 perusal reading assignments left. There's one on rolling motion, which is due Wednesday. I apologize for that one. I realized Saturday that I had somehow the rolling motion perusal assignment had never actually been turned on. So we had to move some things around a little bit. So that one's short notice. So sometime today or tomorrow, do the perusal reading for rolling motion. And then the harmonic motion reading is due Friday, this Friday. And remember, those are the ones that don't have lates. You can't turn them in late. So there's a lot of perusal reading this week, and I apologize for that, but it's just sort of the way things have stacked up. And then we're done with perusal as of Friday morning at 6 a.m. There will be 2 more video experiments. Number 9, which will be on angular momentum, will be posted today. I'm sorry, number 8 is on angular momentum. That'll be posted today. Number 9 on harmonic motion will be posted on Friday. That'll complete all the video experiments. So there'll be 9 of them total for the class. The last thing that you need to do is you need to sign up for a final exam time slot. Those final exam time slots can be signed up for using a doodle poll. I will send out the link again today after class, but just as a reminder, you need to sign up for a final exam slot. About half of the class has done that already, and the other half still needs to. If you're a part of that second half, you can sign up, through next week, but be sure you do it because you cannot pass the class without the final exam. Okay, any questions about any of this stuff? All right. So, as I've mentioned before, I will accept everything except the perusal readings through next Friday, which means that you could, in theory, do all of this on the Thursday before, on Thursday, May 7th, right? And Friday, May 8th. Practically speaking, don't leave it till then. Start now. If you've gotten in a bit of a hole, Now is the time to start digging yourself out.
So after this Friday, no more homework then for Wiley.
So no more homework for Wiley. There is an adaptive practice for chapter 13, which will be due next week. But yeah, the homework is done for Wiley as of this Friday. Well, okay, done as in there will be no more new assignments.
We'll just roll over. Or something.
Yes, it'll just roll over. All right. Let's talk about angular momentum. So actually, let me stop this for a second. And because we're a little behind on the reading, I want to do just a quick intro on what is angular momentum. Okay, so angular momentum is, remember, we've been talking about with rotation, this idea that everything has, in our linear motion examples, has a corresponding idea in rotational motion. So in linear motion, we had something called momentum, right? And it was just mass times velocity. And it was actually the thing that Newton wanted, right? It's the thing that nature really likes. So when we write Newton's second law the way he wrote it, it's the sum of the forces on an object equals the change in momentum over time, right? The time rate of change of momentum. Okay, analogously, angular momentum is the moment of inertia of an object times its angular velocity, okay? Or you can also express it as, for an object moving in a circle, you can express it as the cross product of the radius vector and the momentum vector, okay? These turn out to be analogous things, and you can actually show that. We won't get into it right now, but it's true that the angular momentum, both of these ways of expressing it are the same thing. So the one we're going to focus on is this one, that angular momentum is the moment of inertia of an object times its angular velocity. And the same way that this is sort of the fundamental version of Newton's second law for linear motion, for rotational motion, the fundamental version is the sum of the torques equals the time rate of change of angular momentum. So the angular momentum is a vector, much the same way that momentum is a vector. And the same way that the magnitude of that vector gets scaled by mass for momentum, the magnitude of the angular momentum vector gets scaled by moment of inertia. So if you have an object with a big moment of inertia spinning, it will have a lot of angular momentum. Okay? The velocity gives direction to the momentum vector. So the momentum vector points in the same direction as the velocity. And in this class, now I'm going to be careful there because this is not true of all things, but in this class, the angular momentum vector points in the direction of the angular velocity, okay? If you want the real story on this, you have to come take my junior level mechanics class, because it turns out I'm lying to you right now. But it's a convenient lie for this class. So we're going to work with this, that our angular momentum vector, the direction is determined by our angular velocity vector, okay? Now, just like momentum is a vector, so you can have momentum in all three directions, you can have angular momentum in all three directions. In this class, we're only going to work in one direction at a time for our angular momentum, just like we only work in one direction at a time for angular velocity. But anyone who's ever been in an airplane knows that airplanes can rotate about 3 axes, right? They can do roll, which is, let's see, roll if so I'm my hand is pointed forward, right? Roll is this way. Okay. They can pitch, which is that way, and they can yaw, which is this way. Okay. Roll, pitch, and yaw. Planes can do all three, and that's because there are 3 different ways you can rotate. Okay, so with that quick introduction, I want to come back over here and do a few polling questions. So let me go back to sharing my screen. All right. So we've got a top, and tops are fantastic things. Okay. We spin the top and we look down on it from above. It's spinning counterclockwise. Which direction or directions is or are the angular momentum vector or vectors? And there's the poll. All right, I'll give you another 10 seconds. All right, going once, going twice. Sold. All right, next question. Same top, spinning counterclockwise, but it's slowing down. Okay. In which direction or directions is or are the torque vector or vectors? I'll give you another 10 seconds. Going once, twice. Sold. All right, last one in the sequence. Still spinning counterclockwise and slowing down. Which direction or directions is or are the force vector or vectors responsible for the torque? All right, I'll give you 10 more seconds. Going once, twice. Sold. All right, let's walk back through these three. Okay, so the first one was asking about which direction is or are the angular momentum vectors. So how would we figure this out?
Draw a picture.
Okay, so we got a picture here, right? How do we figure out which way? We know it's rotating, right? It's rotating. If we were looking down on the top of it, it would be rotating counterclockwise, right? So that means that the left side here is moving towards us and the right side is moving away from us, right? That's the sense of it spinning. So how do we figure out which way the angular momentum is going? What sets the direction for the angular momentum vector?
Use the right hand rule.
Okay, we can use the right hand rule, right? If we know which way it's spinning, the right hand rule tells us what?
The angular velocity.
Right. So if it's spinning counterclockwise, right? So it's spinning towards us over here, away from us over there. We make it so our fingers curl that direction, right? And that means our thumb points up. Thumb pointing up means that our angular velocity vector points up, right? So let's draw ourselves an angular velocity vector. That's kind of a lame one. Let's see if I can make it. How do I make it better? Well, there you go. I draw it like that. All right, one more time. Here we go. There we go. That's more my kind of vector. Okay, there's our angular velocity vector, right? Great. But now we want to get to angular momentum. How do we get from angular velocity to angular momentum?
Multiply it by the moment of inertia.
We multiply by the moment of inertia. And just like mass, moment of inertia is a scalar. So it can change the magnitude of our vector, but not the direction, which means that the direction of our angular momentum vector is up everywhere. So the right answer here is A, okay? And this gets at the reason why with spinning objects, it's easier to talk about angular quantities than linear ones, right? We'll see that more here in a minute because the velocity vector, right? The velocity vector on the left side is moving towards you, and the velocity vector on the right side is moving away from you. So every point on this top has a slightly different angular or velocity vector, but it all has the same angular velocity vector, which makes it a lot easier to think about. Okay, so if we go on to the next one here, oh, maybe I have to gotta go back to the mouse. There we go. All right, so now we've got the same thing, right? Except for now it's slowing down. If it's slowing down, how do we figure out which direction the torque is? So let me take a step back. What role does torque play?
It's a change in angular momentum over time.
Right. The torque is the change in angular momentum. So if it's slowing down, is that change negative or positive?
Negative.
Right. So if it's negative, then the torque better be in the opposite direction. So let's draw that. Let's make our torque blue because I feel like torque should be blue today. So that means our torque vector looks like that, right? Maybe. It's kind of clunky. All right, there you go. There's our torque vector. Okay. Our torque vector has to be pointed the opposite direction because just like if you're moving forward, right, you have a forward velocity, but you're slowing down, that means your acceleration is backwards. Here, if our angular momentum is up, but we're slowing down, that means our torque has to be down. Okay, and the last one in this sequence is asking about the forces. Okay, so we've got our angular momentum going up, we've got our torque going down. So in order to have a torque going down on this top, what do the force vectors have to look like?
It would have to be whichever way your fingers curl if you're using the right hand.
Right. We'd have to do that whole right hand rule business again, right? So we can do that, right? So we know our torque is down, right? So that means whatever we do out of this, our thumb has to be pointed down. Okay. And we can draw a radius vector out to the edge of the top, right? So here's the piece to the left-hand side of the top. Okay, so now we have to figure out if our fingers are pointed towards the pink and our thumb is pointed down, which way do our fingers curl on our right hand? So I want you to all do it. Do this, you act like, you know, it makes you feel stupid, but do it anyway. Point your fingers in the direction of the pink arrow. Point your thumb in the direction of the blue arrow. And on your right hand, which way do your fingers have to curl?
Away from us?
Away from you, right? Into the page, into the screen, which means that the answer here is D. They're towards us on the right, away from us on the left. Now, we could do the exact same thing, right? We could go to the other side. So let me erase real quick and get rid of that guy. And let's repeat on the other side. Okay? I draw my radius vector out here. I use my right hand. I need to put my fingers in the direction of the radius vector. Okay? And my thumb in the direction of the torque vector, right? So my fingers pointed along the pink arrow, my thumb pointed along the blue, and which way do my fingers curl? And the answer is you have to kind of like break off your arm and like bend it away from you. But if you do that, right, your fingers pointed to the left, your thumb pointed down, it means that your fingers curl towards you, which means the force vector here on the right side has to be pointed out of the page. Okay? It's really fun. So when you take 204B, 204B has way more cross products than 204A does. Okay? When you take 204B and you're taking a 204B exam sometime, look around the room. It's really kind of funny. You're gonna see a whole class full of people trying to contort their right arm into all kinds of weird ways in order to make the right hand rules work. Okay. All right, questions on this? Okay, I've got one more question for you guys. So that we figured out that these forces have to be opposite the direction of motion, right? Because this thing is spinning towards us on the left, and we just figured out that the force has to be away from us on the left. But it also has to be towards us on the right. So what force would do that? What force would change directions from the left-hand side to the right-hand side of this top?
If I understand correctly, the force that causes the torque.
Right, it's the force that causes torque, but I want to know what force that is. It's got to be something, right? All right, some of you were kids at some point. Can you verify for me that tops do in fact slow down over time?
Yes.
Great. So why did they slow down? We just figured out that you have to have some kind of force that is always a different direction every point around the edge of the circle, right? You have to have a force going one way on one side of the top and the opposite way on the opposite side of the top.
Friction.
Friction.
It's kind of like friction. It turns out for a good top, it's actually not friction. For a good top, it's air resistance. Okay? It's actually drag on the top itself. The top is actually pushing air around, and that drag force is always opposite the direction of the velocity. So as it's pushing the air, it slows down. Okay? You actually do get a little bit from friction right at the point down here. But for a good top on a smooth surface, that friction is minuscule because the amount of area it's actually touching on is really, really small. Okay. Anyway, just a fun little bit of why tops work the way they do. Okay, so let's talk a little more about angular momentum. So the reason we talk about angular momentum is, you may have guessed, it's like momentum. What is cool about momentum? Why do we use it? Because your professor makes you. Okay, but other reasons why we would use momentum over here, linear momentum.
What do you mean? Like, for what applications? Is that what you're asking?
Yeah, I mean, why? I mean, we could multiply a lot of things together and make some new thing, right? We could multiply mass and position together and call that a thing. We could multiply spring constant and acceleration together and call that a thing. But for some reason, we picked these two, mass and velocity, and we multiply them together, and we make this big deal about this thing that comes out called momentum. Why?
I mean, in like cars and boats, it's important.
Why is it important? You're right, it is, but why?
Accidents?
Yeah, because
Accidents?
why? So if you think about a car accident, right? Trying to identify all of the forces on a car during an accident would be a nightmare. But we know that the time rate of change of momentum of an object can only happen by what? How can you change your momentum?
With a force?
with a force. And where do forces come from?
Decrease or increase velocity.
Yeah. But where do forces come from? Can I have a force by myself?
No.
No, right? Newton's third law says forces always come in pairs. So momentum, remember we played this game, you can only change your momentum by getting momentum from something else. Okay? In other words, momentum is a conserved quantity. Okay? You can't get rid of it. You can't make it without giving it to somebody else or taking it from somebody else. Momentum is a conserved quantity. So we don't have to, when we go back to the example of like a car accident, we don't have to worry about all the details of the car accident. All we have to worry about is how much momentum did we have before the car accident? How much momentum do we have after the car accident? And set them equal to each other. Okay? Angular momentum. Anybody want to guess what I'm going to write? If momentum is a conserved quantity, what do you think angular momentum is? Oh, I forgot the
Conserved
momentum part.
quantity.
Angular momentum is also a conserved quantity. Okay. Do you want to know what the hardest place in the solar system to get to is? It's not Pluto. Come on, give me a guess. What's the hardest place to get to in the solar system?
Sun.
The sun. The sun, it's harder to get to the sun than it is to get to Pluto. And here's why. Because if here's the sun and here's us, right, in a nice happy orbit, and we have some momentum, right? Which means we also have some angular momentum because here's our radius vector, right? And we can use our right-hand rule, because we know that angular momentum is the cross product of radius and momentum. So radius, momentum, our angular momentum is up. We have to get rid of that angular momentum in order to get to the sun, because our angular momentum, right? If we want to make our radius very small, what does that mean for our momentum? If we can't change this, can't change L, I want to make R small, that means my momentum has to get really big. Okay? So it turns out that getting to the sun is really hard because your momentum has to get huge. Okay, so you've all seen the thing, right? We're just going to get rid of it. We're going to throw it into the sun. Turns out it would be much easier to throw it completely out of the solar system than it would be to throw something into the sun. The sun is really hard to get to because you have to get rid of your angular momentum to get there. Because if you launch something out of Earth's orbit, all it's going to do is just orbit the sun because it has angular momentum. And that angular momentum says you can't get closer, your radius can't decrease without your momentum increasing. So you're in trouble. You can't get there, right? Turns out NASA currently has a spacecraft that is trying to get to about 5% of the distance between the Earth and the sun, right? Or 0.05 astronomical units is the distance measurement they use. Okay. It's going to take it about 11 years to get there. And it has to do a series of what are called gravity assists with Venus and Mercury to do it. It's really, really hard to get to the sun. And the reason is because angular momentum is a conserved quantity. Okay? So what that means is if you have no torques acting on you, right, then your angular momentum is a constant. Okay? So if the sum of the torques equals 0, then forces, oh, did I drop out?
Yes.
Dang it. All right, where did I drop out at?
You're talking about NASA's probe going to the sun.
Okay. All right, let's come back over here then. So NASA's sending this probe to the sun. It's called the Parker Solar Probe. It can only get there by getting rid of its angular momentum. And it can do that by colliding with Venus and Mercury. Now, when I say colliding, I don't mean physically hitting. I mean interacting with. And that it does through gravity. So it gets close to Venus, close to Mercury, uses those two planets to get rid of a little bit of angular momentum or give a little bit of angular momentum back to those planets and, move along its merry way. But it turns out that's a really, really hard place to go. Okay, so now the problem is that you can only get there, or that if your torques are 0, right? So let's look at the Parker Solar Probe here. It's being acted on by the sun, okay? The only force acting on it when it's far from other planets like Earth or Venus or Mercury is the sun, right? It has a gravitational force from the sun. Why can't the sun's gravity cause a torque? So there's the momentum.
Because it's 90 degrees with, it's 90 degrees to the probe. It's not in the right direction. It's always just pulling it inward. So it can't cause a torque.
Right, because if you remember, okay, so gravity is always pointed inward. By the way, I forgot to mention this earlier. I have officially decided to give up on covering Newtonian gravity in this class, and just saying that hurts my heart because Newtonian gravity is beautiful and wonderful, and you should all spend years studying it. But alas, I had to give up something, and so I gave up Newtonian gravity. It's like selling one of my children. It just feels wrong. Okay, so gravity always points towards the sun, right? So there's our force vector. And if you remember the definition of a torque is the cross product of radius and force vectors. But the radius vector and the force vector are, well, they're anti-parallel, right? But they're pointed in the same direction. So the perpendicular component of the radius vector to the force vector is 0. Or alternatively, the perpendicular component of the force vector to the radius vector is 0. Or alternatively, the angle between them is 180 degrees, and the sine of 180 degrees is 0, right? We could go through all those ways we could calculate cross products. So the sun's gravity can't cause a torque on this probe, which means that the torques are 0, okay? And if the torques add up to 0, that means that the time rate of change of angular momentum is 0. And that means the angular momentum is a constant, okay? So that gets us back to this problem, right? if we want our radius to decrease, our momentum will have to increase. Or alternatively, we can look at it in terms of moment of inertia and angular velocity. So the moment of inertia for a small object very far from a big object is just its mass times the radius of its orbit squared. Okay? So if L is a constant, that means that the mass times the radius squared times the angular velocity is a constant. So that means if you want R to get smaller, omega has to get bigger, has to get a lot bigger, right? Because if you want a radius to cut in half, omega has to get 4 times bigger in order to keep this statement true. So the sun is a bad place to try to use as a disposal. You should, if you want to get rid of something, you should just send it out of the solar system completely. That's easier to do than chucking things into the sun. Okay? So let's see an example of this. Well, let me stop for a sec. Questions? All right, let's do an example. So this is way more fun to do in person, but you know, it is what it is. Instead, we get to watch a professor from Ohio State do this. Okay, so we've got a YouTube video here. Oh, wait, hold on. I always forget this. Okay, I'm going to do that. And there we go. All right, so we're going to watch this lovely video about conservation of angular momentum here.
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get a nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
Okay, I want to watch that one more time.
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get a nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
All right. So here's your, oh wait, I actually don't want to stop sharing my screen. Let's go back and share my screen some more. Okay, so here's the question. Let's say that moving the weights outward, so when he's got the weights, right, the hammers, and he's holding them close to himself, he has some moment of inertia, okay? And then when he moves them outward, that moment of inertia gets bigger. Why?
The radius changes.
The radius of what changes?
Of the system?
Yeah. I mean, but like most of his body stayed in the same spot, right? So like the moment of inertia of his head didn't change, or the moment of inertia of his torso, or the moment of inertia of the stool, those things didn't change at all, right?
His arms, I guess. Just
His arms and
Hammers.
the hammers, right? That's why he was holding hammers, because hammers are big, heavy things that have a big mass, right? And so, and remember, moment of inertia is like mass, right? If I had two objects and I put them together, the mass just is the sum of the two masses, right? If I take a moment of inertia of a professor and plus the moment of inertia of a hammer plus the moment of inertia of another hammer, right? I just get the moment of inertia of the whole system. So what he did by extending out those hammers is he changed the All right, I'm back again. Because for some reason my my internet is just not being cooperative today.
At least you knew you were gone
Yeah.
this time.
Yeah. Last time I didn't even realize it till it dinged at me that I was back. All right, let's come back here, share my screen. Okay, so what I was saying, I think when it cut out was that we can just add moments of inertia, right? So by taking the hammers and moving them outwards, he changed the moment of inertia of the hammers, right? So what we're going to say is that he changed this moment of inertia of the system, right, of himself plus the hammers by 50%. Okay, that's just a guess. So the question is, how does that change the angular velocity of the system, right? Because everything had the same angular velocity. Everything was rotating together. So let's come over here and see if we can figure this out. So if we remember, our moment of inertia was constant. Or I'm sorry, our angular momentum was constant, or pretty close to constant. You'll notice he referenced the friction in the turntable, right? Usually, for most things that a person is going to stand on, you have to have some sort of a turntable, right? And the turntable is basically just a nice set of bearings. And those bearings, while they're pretty close to frictionless, are not frictionless, right? So we have a before here, and we have an after. Before, the guy had, here's the guy on the turntable, and he had the weights right in there, right? And after, he had the weights, or the hammers, they're hammers in this video, out there. Okay, and we're going to say that before his moment of inertia was some I, and afterwards we'll call it I naught and I final. And we know that afterwards his moment of inertia went up by 50%, right? Which means we can write that mathematically as I naught, or 1.5 times I naught is I final, right? Or a cleaner way to write that would be 3 I naught over 2 equals I final. Okay, and if we assume that there was no torque, right? There was a little bit, because there was a little bit of friction and there was some air resistance and, who knows what else. But if we assume there was no torque, the angular momentum before has to be equal to the angular momentum after. So what angular momentum, his angular momentum before was just his initial angular velocity, or initial moment of inertia times his initial angular velocity. And his afterwards is just going to be his final moment of inertia times his final angular velocity. Well, we can combine these two equations. We can get that this would be I naught omega naught over I final is his final angular velocity. And if we take this down here, right, that leads us to I naught omega naught over 3 I naught over 2. Are those initial moment of inertias cancel, and I get 2/3 of his initial angular velocity. So by going from the masses in to the masses out, his angular velocity dropped by 2/3. Okay. Which is how figure skaters do those crazy spins. You guys have all seen figure skaters do crazy spins, right?
Yes.
Great. That's how they do it, is they start spinning with their arms and legs out, and then they pull their arms and legs in, and they start spinning much, much, much faster. Okay? So now here's the question to this. This would work even if there were absolutely no forces, right? This would work even better if we could completely eliminate air resistance and friction and all that stuff. All right, so if we do that, let's calculate the kinetic energy before and after. So what was the kinetic energy before? What kinetic energy did our spinning professor have beforehand? What type of kinetic energy? What are our two possible types of kinetic energy? Sorry, what was that? I missed the.
It had to have been just 1/2 mv squared, wouldn't it?
Well, okay, so there's linear kinetic energy, right? That's 1/2 mv squared. That's the kinetic energy for an object moving in a straight line, right? What about the object or the kinetic energy for a spinning object?
Is it 1/2 I omega squared?
Yeah. So that means beforehand he had 1/2 his moment of inertia times his angular velocity squared. Okay. And afterwards he had 1/2 his moment of inertia times his final angular velocity squared. Okay, so let's plug these in, right? We know what his final angular moment of inertia was. We know what his final angular velocity was. So that means in terms of his initial moment of inertia and his initial angular velocity, right? We can, instead of I final, we can come over here and say, okay, that's 3/2 times his initial moment of inertia. And instead of omega final, we can write 2/3 times his initial angular velocity. what's going to happen here? I've got a 3/2. I've got a 2/3. What's going to happen?
It's not going to be equal.
They're not going to be equal, right? Because I have 1 3/2, but I've got a 2/3 squared. So this is going to come out to be 1/2 times 3/2 times 2/3 times 2/3 times initial angular momentum, or initial moment of inertia, initial angular velocity squared. Okay, so one of the 3/2 is going to take out one of the 2/3. And this 2 is going to cancel with that 2. And I'm going to get that my final kinetic energy is 1/3 I initial moment of inertia, initial angular velocity squared. So how did it change? Which one's bigger?
Initial.
Initial. Okay, so now where did the energy go? Remember I said this would work if we were really like in a vacuum, right? If we were in the middle of nowhere, if there was really no other object for that moment, that energy to go into.
What you did right now earlier, you did all of that just to see the difference in the coefficient, the 1/2 and the 1/3.
Right. To show that this state right here has more kinetic energy than this state. So how do you change kinetic energy? What's required to change the kinetic energy of an object? Because we did, right? We had more kinetic energy over here than over here. So if we go from here to here, we had to change the kinetic energy.
Does it turn into potential energy?
Yeah, you got to do something, right? It's got to be potential energy. It's got to be, or the other option is it could be, we could do work. And it turns out that's what's happened here. It takes energy, it takes work to move these masses from here to here and back. Okay? And in fact, because the final is less than the initial, it took negative work to do this. Right? It took negative work to move the masses outwards. But it would take positive work to do it in. That's why a skater pulling their legs in looks like they're spinning so fast. It's because their energy has actually gone up. They are using their muscles to do work on themselves in order to increase their kinetic energy. Okay? This is a variation of what every kid on a swing set knows. And that is you can do work by pumping your legs in order to make you swing faster. Okay? Same general idea. And this is the trick, because in kinetic energy, right? We've got a moment of inertia. Our moment of inertia can change, right? You can change the moment of inertia for an object by redistributing the mass inside of that object. Just like this professor moved the hammers from here to here, he redistributed his mass, which meant that he changed his moment of inertia, which allowed him to do work on himself in order to make him spin faster. Okay? All right, now that's a lot to process for a minute. So let's step back and think about this. What I just said is that in an isolated system with no torques, angular momentum is conserved. That we can use that to figure out, if we know how the moment of inertia changed, we can figure out how the angular velocity changed. But that change in moment of inertia didn't come for free. It took work to change the moment of inertia. And the work that we did to change the moment of inertia means we either get more or less kinetic energy, depending on if we did positive work or negative work. Okay? All right, how we feeling? All right, let's do one more. And this one's even more fun. Okay? Where'd my cursor go? There it is. Okay, unfortunately, this one, so here's the link. Unfortunately, they made it so that you can't watch this in, oh wait, I'm not showing you the link. The link is in the link is in the slides, which you can get at through the web page, or the Blackboard page. But this is really cool. So here's what we're gonna do. How many of you have seen this before? Anybody ever seen this where you you do the bicycle wheel gyroscope? All right, this is fun. Can
We
you
have
see?
it in 110. If we could get into 110.
I know. I would be doing this in front of you right now if I could. Okay, so here's the way this works. All this is, oh, hold on one second. I need to optimize. There we go. Okay, so I've turned off the sound because the sound is just garbage. It's just static. Okay. All right, so you've got a bicycle wheel hanging from a rope. Okay. He's just going to spin the bicycle wheel. He's going to stand it up, and voila. And you'll notice that it slowly falls back down. So I'm going to go back and we're going to watch that again because it's worth watching again. All right. Now here's your question. Like, what the heck? Why did that bicycle wheel not fall over? Why on earth did that bicycle wheel not fall over?
It has momentum in its rotation that's greater than the gravity trying to pull it down.
Okay. So let's take that apart. What kind of momentum does it have?
Angular momentum?
Right, it's spinning, so it has some angular momentum. And we just said that to change angular momentum, you need what?
Torque.
A torque, right? And angular momentum is a vector. So which way is the angular momentum of the bike tire pointed?
In what position? Like when it's just
What,
hanging?
yeah,
Or
let's
when,
say, well, here, let me actually share my screen again. Let's say, right now, at this point in the video, let's actually get it right. There we go. Which way is the angular momentum vector pointing for this bike tire?
Either away or toward the string.
Yeah, so let's pick one. Let's say it's rotating, I don't know. Let's say it's rotating to the, it's rotating so that its angular momentum vector is pointed this way, right? Which means that if we use our right-hand rule, that means the top of the tire is coming towards us and the bottom of the tire is moving away from us. Okay? So there's its angular momentum vector. If we wanted it to fall over, which way would its angular momentum be pointed if it just fell straight down?
would it be the opposite?
Well,
Wouldn't it be toward us?
if it fell down, right? So if it got to, let me go back here. No, undo that one. If I go back here to where it started, right? Come on, thing. There we go. So if we went back to there, which way would its angular, if it was spinning still, right? Which way would its angular momentum be pointed?
Up or down?
Up or down, right? Which means its angular momentum vector would have to be pointed that way. Okay, let me undo that. Let me make it a different color. I feel like light blue is an excellent color for angular momentum. Have to be pointed that way, right? Okay, so can everybody agree with me that the pink and blue arrows are not the same?
Yes.
Yes, wonderful. So what would it take to make the pink arrow be pointed in the direction of the blue arrow?
Have to rotate it.
You'd have to rotate it. Can you do that? Can you rotate reality? No. So what you actually have to do to turn the pink arrow into the blue arrow is you have to get rid of all of the horizontal component of the pink arrow and give it a whole bunch of vertical components. Okay? So it actually takes a torque, and it takes a torque in two directions to do it. So let's go back to, hold on, I gotta, let's forget this. Let's go back to where I had it. There we go, right there. All right. What forces are acting on this thing?
Gravity and the string.
Gravity and the string, okay. So gravity is pointed down, right? The string is pointed up, and we know that they have to be balanced because it's not accelerating downwards, correct?
Correct.
So now here's the trick. Which direction are the torques from those two forces? Okay, let's draw them out. So, first of all, gravity is the easiest one because where does gravity act?
Down.
Down. And where on the object does it act?
Everywhere.
Everywhere?
Center of mass.
Yeah, it's like it's acting at the center of mass, which conveniently is where this thing is rotating around. So it has no lever arm, no radius vector, which means the gravity can't apply a torque. All right, so what about the rope? Well, the rope isn't acting at the center of mass, right? The rope's radius vector looks like that, right? And which way is the force on the rope, from the rope on the spinning tire?
Upward.
Upward. All right, so you put your fingers in the direction of the orange vector and you're making it curl upwards. Which way does the torque point?
Toward us.
Yeah. Okay, so you have no torque in the direction, in this sideways direction. You have a torque towards us, which is why the thing precesses, right? By precesses, I mean, it doesn't just hold still, it moves around in a circle, right? That's because of the torque from the fact that you have a torque sideways on the thing, right? But you don't have a torque in the direction you need to get rid of your angular velocity, to get rid of your angular momentum. So it can't fall down. It can't fall down because you don't have a torque to make the angular momentum work, which is crazy. Okay. This is how segways work. This is how hoverboards work. This is how spacecraft work. This is why you can ride a bicycle. Okay. You can ride a bicycle because once your tires are spinning, they have angular momentum. And to change that angular momentum, like to tip your bike over, requires a torque. And that's not easy to do. Okay. All right. So this problem, if you want to do this problem for real, you got to take my junior level mechanics class. But this problem, I hope, illustrates to you this concept that angular momentum is a real thing and that it really impacts the way things work. And there are some ways you can demonstrate this that are pretty easy to show, but that you look at and you think that can't be right. That doesn't make any sense. And yet, you just all watch the bike tire do it. Okay. All right. Questions?
Can you explain again, kind of what the string did again to where it's connected to that
Sure.
peg?
Let me clear this off for a second. All right. So here's what we know. We know that we have a force acting upwards on the bar from the string, right? There's our force. There's our force. Let's make it orange. Okay. So there's our force vector going up, right? Let's pick a different color. Let's do light green. Okay. To figure out the torque, we need to figure out the radius vector. The radius from the place where it's rotating, the center of rotation, which is right there. Oh, I want you to a different color. Undo you. There we go. There's our radius vector. Okay. Let's label that guy. All right. So there's our force and radius vectors. Okay, so now we can figure out what the torque is. Well, to do that, we put our fingers in the direction of the radius vector and we curl them towards the force vector. and our thumb points in the direction of the torque.
Would that
So-
be like towards the left or right then?
That would be pointed at you, right? Right out of the screen. Let me change. So this might be kind of hard to see because it'll be small, but can you see my video now?
Yeah.
All right. So your right hand, your fingers need to go in the direction of the radius vector, which is hard to do, right? But it's that way. And you want them to curl in the direction of the force vector, which is up. So my thumb is now pointed right at my face, right? Which means that the torque from this force is pointed out of the screen.
Uh-huh.
Okay, we figured out that we needed to get rid of angular momentum pointed to the right. But my torque is in the wrong direction. My torque is pointed out of the screen. There's no torque pointed to the left or right, which means that I can't get rid of my angular momentum in that direction. So the tire can't fall down because it has angular momentum. And in order to fall down, it has to get rid of that angular momentum in that direction. Okay? Does that make sense?
Yeah, it's a little better now.
Okay. So this is sort of, this is very non-intuitive stuff because you look at that and you say, okay, if I pick up a bike tire and I let it go, it should fall down, right? But it doesn't, as long as it's spinning. And this is why you can ride a bike. It's much easier to balance on a bike when it's moving than it is when it's holding still. Every kid who's ever ridden a bike knows this, right? If you try to balance on a bike when it's holding still, you're going to fall over. If you balance on a bike when it's moving, it's really very easy. And the reason is exactly the same. It's because the spinning bike tires have angular momentum. And to change the angular momentum of the bike tire requires a torque. And a bicycle is designed to have very little torque in the direction the tires are spinning. And so it's hard to fall over on a bicycle. Not impossible, but hard. It takes some doing. Okay? Okay. Does this make sense? A little bit? All right, we'll take a little bit. Okay. I think we better stop there for the day. I think everybody's brain is probably fried and my voice is pretty well shot. So we'll stop there with our bike tire, magical bike tire that floats thing, which, by the way, you guys should try this at some point. You can do it with, just do it with a fidget spinner, right? But if you take a fidget spinner and you spin it, right, you can feel it's hard to turn. That is the same game you're playing. It requires a torque to change the rotation of that fidget spinner from up to sideways or from up to down. All right.
Kind of like a grinder then.
Yes, it's exactly like that. A grinder would have the same properties, right? When you're operating a handheld grinder, it's really awkward to turn, right? Because you're changing you're changing the angular momentum. And
Yeah,
a grinder has a lot of angular momentum.
I prefer to use, like, when I use a grinder, there's like huge big wheel grinders and there's little wheel grinders. The little wheel grinders are way easier to manipulate.
Exactly.
And the big wheel grinder it's hard to get a good grip on it.
Right. It feels like it doesn't want to do what you want it to do, right? And
Yeah.
it's exactly the case because it has a big angular momentum that you have to change every time you want to reorient the thing.
Is it the radius? Because of the radius is larger on the spinning wheel.
Yes. Yeah. Because remember, moment of inertia goes like the radius squared. So if you double the radius, you quadruple the moment of inertia. If you change the moment of inertia, you change the angular momentum. All right. Okay. I'll stop sharing my screen and we'll call that a class. Remember to do the reading, guys. There's reading for Wednesday. So have a read through this and let it percolate into your brains a little further.
Thanks, Dr. Null. Have a good day.
You too. Bye-bye.